Well, thank you for inviting me, and I'll build on some of the other talks that have just been presented. So, two things you should never do with a time series. I haven't learned the lesson yet. Start one or end one. What I'm going to do is I'll start with a little bit of history. For my PhD dissertation, I went back to Peru, to a town that was about 50 kilometers from where I was born, and started a time series that was very high tech. We rented a fishing boat, and there was a dog on there most of the time. We had a manual winch that we lowered bottles over the side and collected samples Monday, Wednesday, and Friday. We took the weekends off, and we did that for a year and a half. And actually, that time series has now been continued by the Peruvian Fisheries Research Institute. And then this is my retirement plan, or the future, where I think we're all going for automated time series. So I wanted to start with the concept of process time series, and that is thinking about the process before you start your time series. And my PhD advisor, Dick Barber, was a man before his time. In fact, some of these ideas are still before their time, I think. We started a couple of time series, one in the Galapagos and one in Paita. I was born in Talara up here. And we wanted to test the hypothesis that propagating physical disturbances that could be very easily measured in sea level could also be measured in biology, because they had biological impacts. And this is the time series collected at Paita during the dissertation, where I plotted sea level at a pier in red during the starting in June of '82 to April of 1984. When I started this time series, I had no idea that the biggest El Nino of the century was going to show up. And then I plotted 60-meter temperatures at this station that's about 15 kilometers from shore. And at the bottom, I've inverted the sea level record, and I plotted nitrate at 60 meters, which is the depth at which upwell waters are brought up from. And our previous speaker told us a very nice story about how the variations in the depth of that nitrocline modify productivity. And the conceptual model for upwelling systems is that during normal conditions, that nutricline is shallow, and a lot of nitrate is brought to the surface, which stimulates productivity. And during El Nino, that nutricline is deep, and we have declining productivity. And as Jennifer Fisher told us, that has dramatic impacts on ecosystem systems. And so the depth of the nutricline is a fundamental property in both upwelling systems and globally. Now let's get to the Monterey Bay time series, which was started about the exact same time as the hot time series. And it combines ship moorings, AUVs, gliders, satellites, and modeling to do its work. It's produced a lot of publications. It generates a lot of ideas. Time series generate ideas and processes, studies. To us, because of our emphasis on technology development, they were a natural laboratory for that. And in my case, my interest was in studying the biological response to climate variability and change. The Monterey Bay has a long history, as we just heard, of Cannery Row. And what I've done here is this station that we occupy, one of the stations we occupy routinely, was occupied early on by Hopkins, right before the sardine boom. Interestingly, during the sardine boom, there was hardly no measurements made in Monterey Bay. And Calcoffee starts when the sardine fishery collapses. And they go away and retreat to the Southern California Bight in about 1980. And this kind of provides you with a history of measurements. And then MBARI is started in 1987, and we filled this in. The point of this figure was to show that even though there is a 0.1 degree C per a decade increase here, most of that increase is really driven by these very large, unusually warm events. Because the temperature back in the 1930s, there are similar temperatures are observed presently. But it's these 82, 83, or 97, 98, and the recent warm events that drive most of this trend. We've heard a lot already about the PDO. This is an image of a North Pacific image of the global PDO, or global ENSO actually. This is the first mode, El Nino. And we in the North Pacific are embedded in this variability. And so we live what's happening in the tropical Pacific. The time series in shade is this higher frequency one. If you do the global PDO analysis, then you get the blue line. And we've already seen these cooler events and these warmer decades here. I'll show you data from, I'll get to this in a second, but also data going further offshore and on a transect that we've done from Monterey to Baja California. This is the main stations of our time series, and the point, an important point, is that space and time are intertwined, especially for biology, and that may lead to some of these changing equations that Ralph Garrigy was talking about. So C1 is in the upwelling shadow. M1 is in the path of the upwelling plume. This is SST, cooler waters. And M2 is starting to get out into further into the California current. Don't try to process all of these. These are smooth seasonal cycles. We sample at about the same frequency of hot, perhaps a little more often. And we take our 30 years or 28 years of data and we smooth them down. And this is our canonical seasonal cycles. Let's look at nitrate. Here's the upwelling cycle with high nitrate at M1. And then look also at, remember M1 is our upwelling site. M2, C1 is in the bay. Highest biomass in the bay, followed by M1 and then further offshore. We measure diatoms in all varieties, and they are the dominant organism in our ecosystem, with dinoflagellates playing a role later on in the year. A couple of other things to note here is that it looks like there's an enhancement of both growth and productivity index at the M1 site where nutrients are optimal, and that's probably due to a combination of both iron and nitrate. We start to look at longer term cycles, and we think about El Nino. El Nino actually, in our part of the world, is centered around our wintertime. And so rather than look at the normal year, we've looked at the El Nino year. And this is what the climatology looks like, and it's our warmest waters are in the fall. And if you look at the first EOF, which is our El Nino signature, you can see that all of that energy is centered towards the winter time of the year, which is our low productivity season. And so El Nino impacts in relative to Peru, for example, where it hits during the high productivity season, are minimized. And when we plot the MEI versus our EOF1 mode, we get a very nice relationship with a few outliers, which are these very warm years we had recently, where perhaps our equations are getting modified. And so there's always strong relations between T and climate, but much less so for biology. I'm not showing you, if I did the same thing for chlorophyll, a regression would be awful. And I'll try to work through why some of that is occurring. Over the course of our 28 years, this was actually made about almost 10 years ago. We probably made over 2,500 measurements of C14 productivity. And there is a lot of noise in this. But if you have the luxury of having a lot of data, you can average them. And then all of a sudden, some patterns show up that are nonlinear in nature, which partly explain why we have this difficulty relating biology to climate, or a much more difficult time. So when waters upwell and are cold, we have very little biomass in our water, therefore productivity in the absolute sense is low. There's a incredibly fast ramp up because conditions are optimal, plants are growing very quickly, and we have high productivity that then decays as we go, as water warms up. You can do the same thing with nitrate. Nitrate is higher here, productivity is lower, and then ramps up and decays in some nonlinear fashion. Same is true with chlorophyll. And again, if we do a relationship between diatoms and primary production, we get a relationship. If you did this with any other taxonomic group that we enumerate, you don't find any relationship. Here's just another example of that. Let's just focus on the black line, which is our measurements of PB opt compared to a standard satellite measurement, either by Betterfield-Falkowski or an Epley curve. And if we remove the temperature effect, we see this enhancement of growth that is occurring at lower temperatures and higher nitrate and higher. It's relatively unimportant for the satellite estimate because this is occurring over a very small area. Okay, let's look at some trends in our time series, and here we're focusing on this period of cooling that has been talked about a couple of times. After the 97, 98, we had this shift, which turns this into a decreasing period of temperature for us from 98 to 2013. If I would have extended this out to include the warm years, our trend is exactly zero. We have no trend in temperature over the course of our time series. And salinity is increasing. Again, as Jennifer and others have said, we get higher salinity waters during low temperature periods. Nitrate is increasing, and both productivity and chlorophyll are increasing. And productivity, in this case, was increasing at about 3% per year. If I extend this out to the present, we're still increasing at about 1 to 1.5% per year. And our productivity is increasing faster than chlorophyll and phytoplankton biomass, which suggests that phytoplankton are growing faster. If we kind of look at this again from this nitrate at 60 meter perspective, and I've just zoomed in on the shift, we have temperature at 60 meters, nitrate at 60 meters, and surface chlorophyll. We see this nice relationship between these two properties, and then an inverse relationship between little things and big things. And so during these colder periods, we tend to have more bigger things in a relative sense, a few microns bigger, and less of the small things. Here is a summary of sort of a wide variety of properties, and I'm going to take you through these, not all of them one at a time, but a few of them. So I think by now you're accustomed to the idea of anomalies. Biologists for years weren't able to do this, remove the mean, remove the seasons from the seasonal mean, which we can do if we have these time series now. And the residuals then here show the 92, 93 El Nino, the 97, 98 El Nino, and our warm blob El Nino combo. And then nitrate at depth being higher during this cooler period and lower. And then the shift towards higher chlorophyll in a later period. And we've also heard about declining oxygen. And this is oxygen now at depth, and I'll show you the detail of the oxygen decline in the next few slides, in one of the next few slides. 26.8 isopycnal is about 300 to 400 meter depth. And there's been this sort of steady decline, which stopped it during our warmer period. And there is Bruce Robeson has a midwater time series, and I'll talk briefly about that. And in this midwater time series, he saw this change to organisms that are better adapted to lower oxygen that then disappear a little bit in here. So that story is still. And then we've been measuring the partial pressure of CO2 on our cruises, and this I think is probably the longest quote-unquote ocean acidification record coastally and maybe globally, which we then can convert to pH, and I'll give you a blow-up of that in a little bit. So this, if you take our oxygen data and we look at the vertical profile of oxygen, this is this black line here. I'll tell you what the dashed line is in a second here. And in the absolute, we have two peaks, and I won't go into the details, but I think we can separate these out in that the shallow one is related to flux, and the deep one is related to ventilation. One of the interesting things in terms of the flux story is that with this, we have this really strong seasonal cycle and productivity. If you looked at the flux at 200 meters, you would hardly see any seasonal cycle at all. And that's one of our conundrums, and we need to work on that a little bit. If we look at the rate of decline percentually, then the maximum is at depth and at about 3% per year. And there is an inkling that there is an increase in oxygen, actually, in the oxygen minimum zone proper. Our oxygen minimum zone is deep, somewhere between 600 to 800 meters. And now I'm going to show you, so if we take two cruises that we did along this transect from Monterey Bay to Cabo San Lucas, and we difference them, this is the plot we get. And those cruises were separated by about a decade. Again, showing this increase in oxygen at depth. So these are our two cruises. If we take the 2012 and subtract 2003, we get this difference with this shallow maximum and this deeper one that is primarily driven probably by flux and by ventilation. If we take the deltas from that for carbon and nitrate and compare them to each other, we see that these changes are occurring at a Redfield ratio, not surprising. So as oxygen is declining, CO2 and nitrate are both increasing, as predicted by Ryszewski and Dunn, and perhaps increasing the productivity of the California current system. They're also increasing, of course, the CO2 content. And if you do a calculation, back of the envelope calculation, this decline in oxygen is increased PCO2 by about 8 ppm per year, which is about 4 times greater than the increase caused by ocean acidification. So I'm not sure what all that means, but that's just the calculation that occurs. And you can see this sort of reflected in our time series of PCO2. This is the same panels that were at the bottom of one of my figures, and I plotted that together with the Mauna Loa record, and you can see how much greater in amplitude the variability in PCO2 is in the ocean than it is in the atmosphere. And you can kind of get an indication that the CO2 levels have been increasing over time as well. And that may be a result of this oxygen decline. But because nitrate is also increasing, the effect of this is really only measured inshore. And as the water is ejected off, CO2 is drawn down to probably the same levels as it had been before. Our pH, of course, is slightly more acidic than hot, and looks like it's declining at a little faster rate. I'm not going to show you any results from this. This may be for another OCB meeting. We're in the process of putting together our different time series. The one from the surface, which is the one I've mainly talked to you about today, the one that Bruce Robeson runs, where he is doing midwater transects and counting midwater biota, and the one by Ken Smith et al., which has also been mentioned as well. And there's some interesting relations between those and climate. And so that's just a teaser for a future talk. What I want to end with is the idea of going to an automated time series, and I'm going to go through just a couple of examples of, I'm out of time, of things. Here is a mooring record of CO2. Here's another trivia question. The slope of this, this is delta PCO2, is exactly 0. Why is this equivalent to the other PCO2 time series that I showed you before? I won't get into that. Here is a record from an ADCP at M1 that starts in 1992 and runs to 2016. One of the interesting things is that this is backscatter, so these reds are high. The highs are all during warmer periods, very near shore, which we think is related to the collapse of this upwelling ecosystem. And since I'm running out of time, I'm going to just try to finish this. We've added PCO2 sensors to wave gliders, and our plan is to replace our ship board PCO2 measurements with those from the wave glider. And we're building long-range AUVs that have been adapted, have ESPs that are adapted to them, as well as other samplers and instruments. People like Kelly Benoit Bird are adding acoustic devices to these. And I think that this will open a new window for observing the sea. Lastly, just a little bit on eDNA that was mentioned earlier, not much. Many of us collect samples and freeze them, not knowing what we would do with them. We took ours out of liquid nitrogen storage and analyzed them for anchovy eDNA, and show that there's a nice correlation between the appearance of whales at our C1 site and anchovy abundances. So I want to finish with the idea of automating this Monterey Bay time series, but also with the idea of our mantra has been to pick locations in the ocean and go back to them repeatedly. If we understand the spatial distribution of our ocean a little bit better, and we have autonomous vehicles that allow us to do that, shouldn't we be sampling the process as opposed to a site? And with that, I'll stop and take questions, since I've already exceeded my allotted time.
Okay, we have time for one quick question.
Thank you, Susanna Mendoza, University of Rhode Island. You suggested that primary production was higher at colder temperatures, but there was a perfect negative correlation between nitrate and temperature. So how can you tell the two apart?
No, so the growth, the prime production isn't higher in absolute terms. It's only the growth. So there's two things intermingled in there. At lower temperatures, water is upwelled, and that water doesn't have any biology in it, and therefore productivity is lower. But the rate at which the organisms are photosynthesizing, the intrinsic rate, is higher. So maybe I didn't explain that.
Yeah.
Mm-hmm.